Welcome to the deep dive.
Yeah.
This is where we try and, get a handle on these massive tech systems. How feasible are they, really?
Yeah, and quickly, right? Without getting totally stuck in all the tiny implementation details from day one.
Exactly. It's kind of the ultimate shortcut, isn't it? If you're, say, an engineer or maybe a product manager.
Or anyone designing something new, really.
Yeah. You need that quick answer. Like, can this thing handle a billion users?
Mm-hmm.
And you need it fast, like in 10 minutes, not 10 months.
Absolutely.
So our deep dive today, it's into something pretty critical for anyone in that position. It's called back-of-the-envelope estimation, BOE for short.
Right, BOE. It's sort of the art of using quick thought experiments, maybe some basic performance numbers you already know.
To figure out if your design can actually handle the load you expect, like the traffic, the data.
Precisely. It's that crucial sanity check. You do it before you start seriously coding anything.
Okay, so our mission today.
Well, we want to unpack the practical steps and also the foundational knowledge you kind of need to do a really solid BOE.
Make it rock solid.
Yeah. We'll look at how to structure your assumptions, how to quickly estimate those key metrics, requests per second, storage needs.
The big ones.
The big ones. And then, crucially, how those huge numbers actually translate into real architectural choices.
And we're going to use a real-world example.
We are. We'll use something massive, like Twitter, to see how this plays out at serious scale.
Okay, so let's start right there. The purpose of BOE, it sounds simple, just quick math. But why is it so essential in modern system design? Why that first step?
Fundamentally, it's about managing risk. It's about making these fast calculations, but, and this is key, they're based on assumptions you state clearly.
Okay.
Before you invest, months, maybe years building some complex service, you absolutely have to have some confidence that the architecture you've picked.
Like the databases, the caches, the servers.
Exactly. That whole mix can actually handle the load, the traffic, the data volume you're anticipating.
So the goal is evaluation. Like, is this design a good fit early on?
That's it, exactly. Quick, effective evaluation. Is it a good fit for the scale? Or do we need to rethink this, maybe pivot completely before we waste a ton of time and money?
And you mentioned assumptions. Our source material really hammered this point.
Yeah.
Communication, transparency. You can't just, pull a number out of a hat.
No, absolutely not. You've got to state your constraints, your variables. What are you basing this calculation on?
These assumptions become the contract almost.
That's a great way to put it. The estimation is only as good, only as useful as the assumptions behind it. If you're assuming, say, 10 million daily active users.
Or maybe the average file upload is 2 megs.
Right. You have to write that down, state it up front. There was an example in the material about a web crawler.
Oh, yeah.
The designer had to explicitly assume two things. First, they needed to download, 1 billion pages a month?
1 billion, yeah. Huge number.
And second, the average page size was 500 kilobytes.
Okay.
Without stating those two numbers clearly, any calculation about bandwidth or storage is just, it's meaningless, isn't it?
Right. Totally arbitrary otherwise. The assumptions are the foundation.
Got it. Okay, so what foundational knowledge do we need then? You can't estimate size and speed if you don't have a feel for the basics, right?
Exactly. You need a feel for the numbers. And that starts with data volume units, the power of 2, basically.
Back to basics. Bytes, kilobyte.
Megabytes, gigabytes, terabytes. And then the really big ones, petabytes, PB.
And it's easy to forget how big those jumps are.
It really is. A megabyte to a gigabyte, that's roughly 1,000 times bigger. A terabyte to a petabyte, another 1,000 times. These aren't small steps.
So when you start hearing numbers in the hundreds of terabytes or even petabytes...
Your alarm bell should be ringing. Instantly, okay, this isn't fitting on one machine or even a few. You're talking sharding, horizontal scaling, distributing that data load. It's a fundamental shift. Okay, so data size is one dimension. What about the other big one? Speed, latency.
Right, latency. Now, the specific numbers, like nanoseconds for a cache hit, they change all the time as hardware gets better.
So memorizing isn't the key.
Not the exact numbers, no, but understanding the relative speeds, that's absolutely crucial. The hierarchy of speed.
What do you mean by hierarchy?
Well, you need to know intuitively that hitting RAM is incredibly fast. We're talking tens of nanoseconds, maybe.
Okay.
Accessing a local SSD, a solid-state drive. Still fast, but now we're in the tens of microseconds, so orders of magnitude slower already.
And then network calls.
Now you're jumping again. A round trip within the same data center, you're probably looking at single-digit milliseconds. maybe low double digits.
Which is way, way slower than RAM.
Massively slower. And if
Yeah.
you have to go across regions or across the public internet, hundreds of milliseconds potentially.
Okay, so that relative difference is what matters for BOE.
Exactly, because if your proposed design needs, say, 10 network hops for every single user request, you've already baked in, what, 10, 20, maybe 50 milliseconds of latency right there before your application even does anything.
Just from the communication overhead.
Precisely. The goal of BOE here is to avoid architectures that just fundamentally break the laws of physics, or at least the laws of computation speed. You should know that fetching data from another continent is orders of magnitude slower than fetching it from local cache.
And that knowledge directly informs things like, do I need a CDN? Do I need a distributed cache?
Right from the start. Those decisions often become obvious once you consider the latency implications suggested by your rough design.
Okay, latency and data volume. What about reliability? Availability? The nines? That's got to factor in, right? You need a budget for keeping the system up.
Oh, absolutely. High availability, usually measured in those nines, is critical because your estimate isn't just about servers and storage, it's about the redundancy needed to meet an uptime target.
And that's usually expressed as a percentage.
Yeah, a percentage of uptime. 100% means zero downtime, which is practically impossible, of course. Most cloud providers, they offer service level agreements, SLAs.
Right, I've seen those, like 99.9% or something.
Exactly. 3 nines, 99.9%. Or maybe 4 nines, 99.99%. And the difference between those nines in terms of actual allowed downtime per year, it's often way more dramatic than people realize.
Okay, break it down for us. 3 nines,
Yeah.
99.9%. What does that mean in minutes or hours per year?
3 nines gives you about 8 hours and 45 minutes of total downtime allowed per year.
Okay, over 8 hours. Maybe acceptable for some things.
Yeah, for maybe internal tools or non-critical stuff, that might be fine. But if you're running, say, a payment system or a major social network, 8 hours is probably not okay.
Right, definitely not. So what about 4 nines, 99.99%?
Now it gets serious. 4 nines drops your acceptable downtime budget for the entire year to just 52 minutes and 35 seconds.
Oh, wow, less than an hour for the whole year.
Think about that. Any planned maintenance, any unexpected outage, it all has to fit within that tiny window.
Is that level, 4 nines, only for things like finance? Or do big social platforms aim for that too? Seems incredibly hard.
Well, they might aim for it, even if hitting it perfectly is aspirational. But setting that target forces major architectural decisions right from the start.
Like what?
To even get close to 4 nines, you need automated failover everywhere, hot standby services ready to take over instantly, redundancy at every single layer of your stack.
And 5 nines, 99.999%. That sounds almost mythical.
It practically is. 5 nines is just over 5 minutes of downtime per year. To achieve that, you're often talking active deployments across multiple geographically separate data centers. Insanely complex and expensive.
So the point is, the moment someone says we need 4 nines, your BOE has to reflect the cost and complexity of achieving that.
Absolutely. It implicitly demands things like multi-master replication, sophisticated fault tolerance. It's baked into the requirement. And that understanding needs to be there during the initial estimation.
Okay, that makes sense. So let's get practical. How do we actually do this? How do we turn those user goals into numbers we can work with? You mentioned steps.
Yeah. There are a few key techniques, and the very first one, the absolute foundation, is write down and label your assumptions.
We keep coming back to assumptions.
Because they're everything. You must state explicitly what you're basing your numbers on. Are you assuming 10 million daily users? Okay, write it down. DAU equals 10 million.
What else? Average request size, cache hit rate.
All of it. QPS, storage needs per user, cache size assumptions, maybe even initial guesses about server count per task. These are the inputs. They drive everything else.
And it protects you later, right? If someone says your estimate seems off,
you can point right back to the assumptions. Well, we assume 10 million DAU. If it's actually 50 million, then yes, these numbers need to change. It makes the discussion objective based on the inputs.
Removes the guesswork, or at least makes the guesses explicit.
Exactly. And that ties into the second tip. Use rounding and approximation.
Ah, okay, so we don't need perfect precision here.
Not at this stage. Remember the goal. Feasibility. Orders of magnitude. Are we talking 10 servers or 10,000? That's the kind of question BOE answers.
So if the calculation gives you like 11,876 requests per second.
Just round it. Call it 12,000. Or maybe even 10,000 if you want to work with powers of 10. Whether the exact number is 11,800 something or 12,000 doesn't change the fundamental architectural need,
Which is?
which is, wow, that's a lot of requests. We definitely need serious horizontal scaling and load balancing. The core insight remains the same.
It makes the math faster, easier to communicate.
Much faster. Don't get bogged down in pointless precision early on. Nail the ballpark figure first.
Okay, assumptions clear, rounding allowed. What's next? Tip 3.
Tip 3 is about sequence. Estimate key metrics in order. There's a logical flow.
You can't just jump straight to storage needs.
Well, you could try, but it makes more sense to start with the thing that drives your front-end server load. And that's usually requests per second, RPS, or queries per second, QPS.
Okay, QPS. How many requests hitting the system every second?
Exactly. It's the flow rate of user activity. The calculation itself is usually pretty straightforward. You figure out the total number of operations or requests happening over a period.
Like per day.
Per day is common, yeah. And then you divide that total by the number of seconds in that period.
Okay, let's try a quick example. Say 100 million daily active users, DAU.
Okay. 100 million DAU.
And let's assume each user does maybe 10 things a day, reads, writes, refreshes, just 10 actions total.
Right. So total operations per day is 100 million users times 10 actions each. That's 1 billion operations per day.
Okay, 1 billion. Now divide by seconds in a day.
Yep. There are 86,400 seconds in a day. So 1 billion divided by 86,400. That gives you an average QPS of roughly, let me see, around 11,574 requests per second.
Okay, around 11.5K QPS on average. But you hear people talk about peak QPS too. Why isn't average enough?
Because traffic is never perfectly smooth, right? People wake up, check their phones, lunchtime rush, evening peaks. You get these huge spikes in activity.
So the average doesn't capture the real stress on the system.
Exactly. The average load isn't what breaks things. The sudden peaks are. So a common rule of thumb, a heuristic, is to estimate the peak QPS as maybe double the average QPS.
Just double it. Is that reliable?
It's a starting point. Often 2x, sometimes maybe 4x, depending on the application's nature. It accounts for those bursts and some basic queuing theory principles if you only provision for the average.
Any spike causes delays and problems.
Right. Requests back up, latency shoots up. So that peak QPS figure, maybe 24,000 in our example, that's the number your system really needs to handle gracefully. It tells you how many servers you need, what your auto-scaling triggers should be.
Got it. So QPS first, including the peak. Then what?
Then you usually move on to storage requirements. This really dictates your data layer design. What kind of database? How do you shard it? What's your backup strategy?
And the calculation here is?
The basic idea is figure out how much new data comes in each day, your daily data volume. Then multiply that by how long you need to keep the data. 5 years, 10 years.
Okay, seems simple enough. Daily volume times duration.
Well, hold on. It's a bit more complex than just the raw data. You have to consider overhead.
Overhead, like what?
Think about replication. If you need high availability, you might store 3 copies of everything. So your actual storage need is 3x the raw data size, right off the bat.
Good point. Triple the storage.
And then there's indexing. To make data searchable quickly, databases build indexes. Those indexes take up space too, sometimes a lot of space.
And metadata.
Metadata, yeah. Information about the data. So when you do your BOE for storage, you often need a multiplier. Maybe 2x, 3x, even more sometimes, applied to that raw daily volume before you multiply by the number of years.
Okay, that's a crucial detail. Don't just calculate raw data size, factor in replication and indexing overhead.
Right.
What else?
Bandwidth, network bandwidth, the flow rate in and out.
Ingress and egress.
Exactly. How much data are you writing into the system, ingress, and how much are you reading out, egress? You calculate this based on your daily data volumes, again, dividing by the seconds in a day.
And that gives you gigabytes per second, or something like that.
Yeah, usually GBs or GBPs. And that number immediately tells you about costs. Network bandwidth, especially egress, can be really expensive.
And it forces certain design choices, too.
Absolutely. If you have massive egress bandwidth needs, you know you'll need content delivery networks, CDNs, to cache static files closer to users and offload traffic from your core data centers. It becomes non-negotiable.
Okay, so we have QPS, storage bandwidth.
Yeah.
Which leads us to the final tip.
Tip 4, evaluating server count and capacity. All those numbers we just calculated, the QPS, the terabytes or petabytes, the gigabytes per second, they directly inform how much hardware you need and how it should be structured.
The numbers drive the architecture.
Precisely. High QPS, that screams horizontal scaling. Lots of web servers, lots of app servers behind sophisticated load balancers.
Petabytes of storage.
That screams sharding. Partitioning your data across many, many database machines or using specialized large-scale storage systems, no single machine can handle that. The numbers dictate the pattern.
And this is where that classic scaling dilemma comes in, right? Vertical versus horizontal.
Yep. Vertical scaling, making one server bigger and bigger with more CPU, more RAM, it's simpler initially. But you hit hard limits, and it gets incredibly expensive at the high end.
So for massive scale.
You almost always end up with horizontal scaling, spreading the load across many cheaper commodity machines. It's the only way to handle truly massive scale.
But it's more complex.
Oh, way more complex. That's the trade-off.
What kind of complexity are we talking about?
Well, suddenly you have thousands of machines. Things are failing all the time. One server is always down somewhere. So you need systems to handle that automatically.
Failure domains.
Failure domains, yeah. You worry about distributed consensus, getting all these machines to agree on state. You deal with eventual consistency. Data updates might take time to propagate everywhere.
And things like hotkeys, where one piece of data gets hammered.
Exactly. Uneven load distribution becomes a huge problem. You might need complex resharding strategies. It's a whole world of distributed systems challenges. But the BOE numbers, the sheer scale they reveal, often force you down that path whether you like it or not.
Okay, theory is great, but let's make this concrete. Let's walk through that Twitter example you mentioned. Apply these techniques to estimate its QPS and storage.
Sounds good. So step 1, assumptions. We need to define our hypothetical Twitter.
Right, user base.
Let's start with daily active users, DAU. Let's pick a number, say 200 million DAU. Seems reasonable for a large platform.
Okay, 200 million daily users. What about their activity? What do they do?
Good question. We need an activity profile. Let's assume, on average, each user reads stuff like scrolls their feed, clicks on profiles, maybe 4 times a day.
4 reads per user per day.
Okay, and let's say they write stuff less often. Maybe post a tweet, like something, retweet. Let's average that out to, say, 0.5 writes per user per day. Half a write action.
So 4 reads plus 0.5 writes equals 4.5 total actions per user per day, on average.
Yeah, let's go with that. 4.5 actions per user per day.
Okay, now let's calculate the request per second, RPS. Tip 3, total operations first.
Right. 200 million DAU times 4.5 actions per user per day. That's 900 million total operations daily.
900 million. Now divide by seconds in a day, 86,400.
Yep. 900 million divided by 86,400. That comes out to approximately 10,416 requests per second on average.
Okay, average QPS around 10.4K.
Wait.
Now apply tip 2, rounding, and the peak heuristic from tip 3.
Right. Let's round that 10.4K up to, say, 12,000 RPS for easier math. That's our average QPS estimate.
12K average. And the peak. Double it.
Let's use the 2x rule for now. So peak QPS would be 24,000 RPS.
24,000 requests hitting the system every second during peak times.
Exactly. And that number, 12K average, 24K peak, it immediately tells you something profound about the architecture. You cannot serve this with one server, or 10, or probably even 50. This demands a massive, distributed, horizontally scaled system right from the get-go. Hundreds, maybe thousands of application servers, sophisticated load balancing, probably multiple data centers for redundancy.
Yeah, comparing that 12K QPS to maybe a typical company internal app that runs at, 100 RPS, it's a completely different world.
Entirely different scale. It forces you into that complex horizontal architecture we talked about.
Okay, QPS is huge. Now let's tackle storage requirements. This could get scary.
It usually does at this scale. We know Twitter involves text, but also lots of media, images, videos that dominate storage.
Right. So what's our assumption for data generated per user per day?
This one's trickier. Let's average it out, including text, metadata, maybe some compressed media links or thumbnails. Let's estimate maybe 2.5 kilobytes per user per day on average, covering all their write activity and associated data.
2.5 KDB per user per day. Okay, now calculate the total daily volume.
200 million DAU times 2.5 KBDs per user. That gives us 500 million kilobytes, which is 500,000 megabytes. Or 500 gigabytes. No, wait. 200 million, 2.5 kbps equals 500 billion. Bytes equals 500 gigabytes equals 0.5 terabytes. Okay, let's recheck that. 200 D6 users, 2.5 E3 byte user, up to 500 D9 bytes equals 500 gigabytes per day. That seems low for media. Let's reconsider the assumption. Maybe the writes generate text and metadata, but the media is separate. Let's assume the text metadata is small, but media uploads add significant volume. Say 10% of users upload 1 2 MB photo per day.
Okay, let's try that. 10% of 200 million users equals 20 M users, each uploads 2 MB.
So 20 million users, 2 megabytes equals 40 million megabytes equals 100 million, and maybe it's 100 TB per day for video.
Okay, so 40 TB photos plus 100 TB videos is 140 TB per day just for media uploads. Let's add maybe 10 TB for tweets, metadata, likes, etc. So call it 150 TB of raw data ingress per day. Let's adjust our previous assumption.
Okay, 150 TB per day. That feels more plausible with media. Now, apply the overhead factor, replication. Right, let's assume 3x replication for durability and availability. So 150 TB raw data, 3 equals 450 TB of physical storage needed just for today's data. Nearly half a petabyte per day allocated.
Wow. Okay, half a petabyte allocated daily. But we need to think long term. What about keeping this data for, say, 10 years?
Okay, let's extrapolate the raw 150 TB daily volume. 150 TB day, 365 days year, 10 years.
That's a 150, 300, and 650, 547,500 TB.
Which is 547.5 petabytes of raw data storage over 10 years.
Good grief, over half an exabyte of raw data.
And remember, that's raw. With 3x replication, you're looking at needing well over 1.5 exabytes of physical storage capacity. Maybe closer to 1.6, 1.7 exabytes?
Exabytes, okay. That number hitting petabytes and exabytes, that absolutely forces architectural decisions, doesn't it?
It absolutely does. You simply cannot manage exabytes efficiently in traditional relational databases, even heavily sharded ones. The operational overhead, the cost, the query complexity at that scale, it's prohibitive.
What's the implication?
It confirms that the vast majority of this storage, the stuff driving these huge numbers, must be media files, images, videos, and those have to go into specialized object storage systems.
Like Amazon S3 or Azure Blob Storage or Google Cloud Storage.
Exactly. Those systems are designed precisely for this scale. They trade off some database features like instant consistency or complex querying for massive scalability, durability, and cost-effectiveness for large binary objects. The BE storage number makes object storage mandatory.
Okay, storage is mind-boggling. Let's quickly touch on bandwidth requirements. If we're ingesting 150 TB of raw data daily, what kind of pipe do we need?
All right, 150 TB per day. Divide by 86,400 seconds, 150 E12 bytes, 8,400 seconds. That's about 1.74 E9 byte second, or roughly 1.74 gigabytes per second sustained ingress bandwidth.
Just for the writes, the upload.
Just for the ingress, yeah. The egress, serving all that content out to 200 million users reading their feeds. That could easily be 10x, 20x, maybe even 100x higher, depending on the read patterns and media views.
So even just the 1.74 gigabytes ingress is significant. What does that number tell a designer?
It tells them they need serious network infrastructure, high-throughput connections, peering agreements with ISPs, and again, it screams CDN. You absolutely must push static assets, images, videos out to a content delivery network to handle the massive egress load and keep latency down for users globally. It's not optional at this scale.
Okay, so we've got the big numbers. 12K RPS average, 24K peak, 550 PB raw storage over 10 years, 1.5 plus EB physical, 1.7 plus GB's ingress bandwidth, much more egress. How do these numbers directly shape the final design choices?
They dictate almost everything. Let's think about reads versus writes. We assumed 4 reads per user, but only 0.5 writes. That's an 8.1 read-write ratio in terms of actions. But if reads involve fetching many tweets images, the data ratio is heavily skewed towards reads.
So read-heavy workload, what does that imply?
Aggressive caching. You absolutely need to cache frequently accessed data, user timelines, popular tweets, media files, anything you can serve from a fast cache like Redis or Memcache instead of hitting slower backend storage will drastically improve performance and reduce load.
And given that high read volume, what about how tweets are delivered? That fan-out question.
Yes. The classic Twitter architecture question. Fan out on write or fan out on read?
Explain that quickly.
Fan out on read means when you view your timeline, the system goes and fetches the latest tweets from everyone you follow, combines them, ranks them, and sends them back. Simpler write path, potentially slow read path.
Where's fan out on write?
Fan out on write means when someone you follow posts a tweet, the system immediately pushes that tweet into your pre-computed timeline, often stored in a cache. The write path is much more complex and resource-intensive, but the read path becomes super fast. Just grab the already prepared timeline.
Well, which way does our BD point? 12K RPS average, 24K peak.
That huge read volume, the QPS number, strongly suggests you need reads to be incredibly fast. This pushes heavily towards a fan-out-on-write model, at least for the core timeline. You pay the price on the right side to ensure that reading the feed is near instantaneous for millions of users concurrently. The QPS number forces that complexity.
Okay. And what about the servers actually handling those 24,000 requests per second at peak?
They have to be stateless. Absolutely critical.
We need?
Meaning the web or application servers themselves don't store any critical user session data or state locally. All that state is pushed out to a shared, scalable data store, maybe a distributed cache, maybe a database,
Why is that so important?
because it lets you treat the servers like cattle, not pets. If one server dies, who cares? The load balancer just sends the next request to another identical server, which can fetch the necessary state from the shared store. It makes horizontal scaling and handling failures much, much easier. You can add or remove servers easily based on load. That 24K peak QPS demands this statelessness.
So yeah, every single number, QPS, petabytes, gigabytes, second, it acts like a forcing function, pushing the design toward specific patterns like object storage, fan out on write, caching, stateless services, CDNs.
Exactly. The BOE isn't just about calculating resources, it's about discovering the fundamental shape the architecture must take to even stand a chance at handling the required scale. #outro. So when you boil it all down, this whole exercise, back of the envelope estimation, it's really the bridge, isn't it? It translates that fuzzy user activity, scrolling a feed, uploading a photo into hard, quantifiable technical requirements.
Yeah, suddenly it's not just lots of users, it's 12,000 requests per second. It's not lots of data, it's hundreds of petabytes. It's not fast, it's P99 latency under 200 milliseconds.
And having those concrete numbers changes the conversation entirely. You move past vague wishes into actual engineering trade-offs based on scale.
It forces you to get real fast.
But here's the interesting thing the source material touches on. Even if you nail these value numbers perfectly, the real fun starts when the system goes live.
Because things break.
Because things always break, especially at this kind of scale. Failures aren't exceptions, they're routine. Servers fail, networks glitch, data centers have issues.
So the system has to be built to withstand that from the start. Fault tolerance.
Exactly. And this ties back to BOE in a subtle way.
How so?
Well, we'll leave you, the listener, with this thought. When your initial BOE spits out numbers like 1.5 exabytes of physical storage or tens of thousands of QPS, it's not just telling you to buy a lot of hardware. It's implicitly demanding resilience. It's telling you that failure is inevitable at that scale, so you must design for it from day one.
So the sheer scale revealed by the BOE forces you to think about redundancy, replication, automated failover, monitoring, all that fault tolerance stuff.
Precisely. You can't operate at petabyte scale without assuming things will fail. So the estimation itself, by revealing the magnitude of the challenge, forces you to build in that resilience, that fault tolerance, right from the very first architectural sketch. The envelope doesn't just estimate resources, it implicitly demands robustness.
That's a great way to think about it. The numbers force you to design for the messy reality, not just the ideal path.
That's the true power of the envelope.
Fantastic. Well, that wraps up this deep dive. Thanks for listening.
See you next time.